Welcome to Calculus. I'm Professor Greist. We're about to begin the course, Calculus in a Single Variable.
Welcome to Calculus. I'm Professor Greist, and for the next 13 weeks, I'll be your calculus professor. Calculus is a wonderful subject, one of the loftiest achievements of human thought, with thousands of years in the making. Whether you're at the beginning of your studies, or whether you've come back to deepen your understanding, my course will give you a novel experience. This course is built on the main objects of calculus: functions, limits, derivatives, and integrals, both continuous and discrete. You'll learn how to compute with these objects, but you'll also learn what they mean and how they are useful in the engineering, biological, social, and physical sciences. Are you ready? Let's go!
You may be wondering, what do you need in order to be successful in this course? Well, there are several things that you do not need. You don't need a big calculus book. You don't need a fancy calculator. You don't need any money. This is a free course. But there is one thing that you do need a lot of, and that is time. Mathematics is difficult, and it takes time to work through the homework assignments, to think about what you're doing. This is a hard course, and you're going to need time and perseverance to get through it. You're also going to need prerequisites. It's assumed that you know the basics, such as algebra. You need to be very familiar with how exponents work, how polynomials are factored. Sometimes we'll be doing some of the basic algebra off-screen, and it's going to be up to you to fill those steps in. You're going to have some background in basic geometry, knowing about things like curves, circles, volumes, areas of basic shapes. You're going to want to make sure that you've seen some trigonometry before. We'll be reviewing things like sine, cosine, and tangent, but you will need to have some prior exposure. Likewise, in pre-calculus, it's assumed that you've seen the exponential function e to the x and the natural logarithm ln of x. We'll review this a little bit, but you're going to want to make sure that it's not your first time seeing that. And even though this is a calculus course, it is not your first calculus course. I'm going to assume that you've seen some of the basics, such as differentiation or integration of polynomials and exponential functions before. You need to know, or at least have seen, a definition of a derivative, maybe in terms of slopes. And it will be helpful if you've seen a definition of an integral in terms of, say, area under a curve. Now, we're going to go through all of that material again and make your understanding deeper and clearer. But if it's your first time seeing this, then this might not be the course for you. Let's continue with an overview of the course, what you're going to see over the next 13 weeks. The course is broken into 5 chapters. The first chapter is on functions, and beginning with the simple function e to the x, we're going to reconsider functions from the perspective of series, Taylor series, to be precise. We'll learn a new asymptotic language for understanding growth. Then, in Chapter 2, we'll put that language and that intuition to work by reconsidering rates of change and our notion of differentiation. From there, we'll turn in Chapter 3 to the notion of an antiderivative, that is, an integral. Motivated by applied problems in differential equations, we will build up integrals, both indefinite and then definite. In Chapter 4, we'll take what we've learned about derivatives and integrals and put them to use, considering applications in the physical, social, engineering, and biological sciences. Finally, in Chapter 5, we'll revisit everything that we have done in the course, rebuilding calculus in a discrete setting, a calculus for sequences. Your next step should be to take the diagnostic exam and see if you remember all of those prerequisites. Then, begin with Lecture 1. Watch the lecture and then go to the homework assignments. There are 2 homework sets per lecture. One, a set of core or basic problems, and then a set of challenge problems that are optional for those who want to go deeper. Now, when you get to the homeworks, you may or may not encounter some difficulty. If you do, we have several resources available. You can go to the PennCalc Wiki, which operates something like a text for the course. But even better, you can go to the discussion forums. Help and be helped by other people. As you complete homework assignments, move on to the next lectures and repeat. When you get to the end of a chapter, then there will be a quiz. Those happen at particular times. You can see the schedule on the website for the course. Eventually, when we're done with all 5 chapters, we'll get to the final exam, and if you make it to the end, you will be done. It is by no means an easy path to get to the end of this course. It is a difficult subject and is only learned by means of hard work. You are going to have to work hard and persevere to get to the end, but I am confident that together we can make it.
It's a privilege for me to be your calculus professor this term, and I'm glad that you've chosen this course. I want you to make it to the end. Your next step should be to take the diagnostic exam and make sure that this is the right place. Then, start with Lesson 1 and move lesson by lesson. Don't skip around a lot. This course has a flow. Calculus is like an epic story with main characters, grand themes, struggle, and eventual achievement. I want you to see that story. I want you to live that story. This course is going to be an odyssey, a long and difficult journey. But if you work hard, you'll make it to the end with something you can be really proud of, a mastery of calculus.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 1 on functions.
Welcome to Chapter 1. Every story begins with a cast of characters. In this story of calculus, our characters are functions, and the plot revolves around how these functions interact with each other and what characterizes them, from the local workings of their inner behaviors to the global sweep of their asymptotics. This lesson and this course begin with functions.
Calculus is all about functions, and indeed, that is where this course begins. Now, you're probably used to thinking about functions in terms of their graphs that pair x with f of x for a function f. One can also take a more mechanistic view, where x is considered as an input to f, and f of x is considered as the output. Indeed, visualizing this as a machine is extremely helpful, where one feeds x into f and receives as an output f of x. With this in mind, certain terminology about functions becomes natural. For example, the domain of a function f consists of all possible inputs, all the things you might put into the function. The range of a function f consists of all possible outputs. things you might receive from f. Now this is single variable calculus, and because of that, our domains and our ranges are going to be relatively simple. They are going to consist of either the real number line or certain subintervals thereof. Certain operations on functions become critical. Perhaps the most important is that of composition. F composed with g. This is the function that takes as its input x and returns its output, denoted f composed with g of x, and that is g of x fed into the function f. We say f of g of x. One can visualize this as chaining together the functions f and g in the proper order. G comes first, and then f. For example, if one considers the function square root of 1 minus x squared, how can one decompose this into the composition of f and g? Well, f, in this case, would be the function that is on the outside, or that is done last. This is the square root function. G, that which comes first, is what is on the inside of the square root function, namely g of x equals 1 minus x squared. One additional important operation on functions is that of inverse. The inverse of a function f is denoted f with a superscript -1. Don't let that fool you. That does not mean you take the reciprocal of f of x. Indeed, f inverse of x is defined as that function which takes as its input x and returns as an output f inverse of x, such that if one composes with f, one gets back the original value of x for all such x. And now, one can also run this in reverse. If you do f first and then f inverse, one again obtains x. That means that intuitively, f inverse is the machine that undoes whatever f does. Let's look at a specific example where we take as f the function x cubed. What would the inverse of this be? Well, it has to be a function that undoes whatever x cubed does. This is, as you may have guessed, x to the 1/3 power, or the cube root of x. Now, there are several ways to see why this is right. One is that in taking the inverse, we are reversing the role of the input and the output. Or geometrically, we are flipping the graph of this function along the diagonal line, where the input and the output are equal. Of course, we can also think in terms of what the inverse has to satisfy. If we do x cubed and then take its cube root, we get x. Or the other way around, if we take the cube root of x and cube it, we get x. Certain classes of functions wind up being extremely important throughout calculus. Perhaps the simplest such class is that of the polynomials. That is, functions of the form a constant plus a constant times x plus a constant times x squared, all the way up to some finite degree, constant times x to the n. That largest power of x is called the degree. There is a summation notation that makes writing out polynomials very simple. We use the Greek capital sigma and write a polynomial as the sum, sigma, as k goes from 0 to n of c sub k times x to the k. Here, the c k's are coefficients, or constants. Another class of commonly observed functions are the rational functions. These are functions of the form p of x over q of x, where p and q are polynomials. Simple examples like 3x minus 1 over x squared plus x minus 6. are very common throughout mathematics and its applications. Rational functions are very nice to work with. You do, however, have to be careful of what happens in the denominator when you try to plug in a value of x that evaluates the denominator to 0. Your function is not necessarily well defined at such a point. Other powers besides integer powers are important and prevalent. I'm guessing that you all know what x to the 0 is. That is, of course, equal to 1. What is x to the minus 1/2? Recall that fractional powers connote roots, and negative powers mean that you take the reciprocal, so that x to the negative 1/2 is 1 over the square root of x. And what is x to the 22/7? Well, break this up into pieces. First, we take x to the 22nd power, and then we take the 7th root of x. Lastly, what is x to the pi? Well, we're not going to answer that quite yet, but you may have a guess, especially considering the fact that there are rational numbers that are very close to the irrational number pi. Trigonometric functions are extremely common and important. You should already know a bit about sine and cosine. Let's review perhaps the most important of the trigonometric identities. That is, cosine squared plus sine squared equals 1. There are several ways to interpret this. You've seen the interpretation involving a right triangle with hypotenuse equal to 1 and with angle set to theta. Then, in this case, the sine of theta is the length of the opposite edge to theta, and the cosine of theta is the length of the adjacent edge. If we think of those as x and y coordinates respectively, then we see that there's a relationship between this trigonometric identity and the equation for the circle x squared plus y squared equals 1. And indeed, if we think of what happens when we move a point along a unit circle, rotating it by an angle theta from the positive x-axis, then the x and y coordinates of that point on the unit circle are precisely the cosine and the sine, respectively. Other trigonometric functions are common and important. I'm sure you recall the tangent as the ratio of the sine to the cosine function, and its reciprocal, the cotangent function. One can also take reciprocals of cosine, obtaining the secant function, and of sine, obtaining the cosecant function, respectively. Now, all of these that involve ratios wind up having vertical asymptotes in their graphs, that is, places where the function is undefined when the denominator goes to 0. The inverse of the trigonometric functions are very useful, but somewhat treacherous. You've got to be careful. Some students like to write the inverse of sine as sine with a -1 superscript. That can lead to some confusion, thinking that it is the cosecant or the reciprocal of sine. That is unfortunate notation, and I encourage you to use instead arcsine to denote the inverse of the sine function. The arcsine is that function which, when composed with sine, gives you the identity back. One of the things that you'll note about both the arcsine and the arccosine is that they have a restricted domain. The domain must be the closed interval from -1 to 1, because, of course, sine and cosine can only take values in that interval. In contrast to this, the arctangent function does have an infinite domain. Its range, however, is limited between -pi/2 and pi/2. These are all functions that you're going to want to be familiar with for moving forward in calculus. The last class of functions that is of critical importance are the exponential functions. These are functions of the form e to the x, e to the x being the canonical example of an exponential function. Its inverse is the logarithm, or more precisely, the natural logarithm, ln of x. You've seen these functions before. You know, because they're inverses, that their graphs have this symmetry about the diagonal. So, for example, if e to the 0 is 1, as it must be, then log of 1 must be equal to 0, certainly. The question that is often unanswered in pre-calculus or even elementary calculus courses is, what is e, and why is it so important in this exponential function? Well, one could say that e is that value whose logarithm is equal to 1. But since we've defined the natural logarithm in terms of base e, that's a bit of circular reasoning. How do we reason about e? Well, certainly, e is a number. It is a particular location on the real number line. It has a decimal expansion, but being irrational, it is a little bit hard to remember all of it. That doesn't really answer the question of what is e. Why is it so important? Before we get to the answer to that, let's review some of the algebraic properties associated with the exponential function. I hope you remember that e to the x times e to the y is e to the x plus y, the exponents add, and e to the x raised to the y power is e to the x times y. In your prior exposure to calculus, I'm sure that you've seen some of the differential and integral properties of this function. E to the x has this wonderful property that it is its own derivative, and, of course, that it is its own integral, at least up to a constant. These facts are easy to remember, but maybe not so easy to fully comprehend. There is one last ingredient that we're going to need before we go deep into exploring what e to the x means. This is something called Euler's formula. This is simple looking. It states that e to the I times x equals cosine of x plus I times sine of x. This is a wonderful formula. Whatever it means. What does it mean? What is this I that is in here? I am sure that you've seen before the notation for the square root of -1 for the primal imaginary number I. That is what is meant in Euler's formula. It has the property, of course, that I squared is equal to -1. Well, this is a formula. It's a true statement. But what does it mean? Well, that is the subject for our next lesson.
And so we end with a mystery about the exponential function and what it means to exponentiate something that is not a real number. In our next lesson, we'll resolve this mystery, in part, by contemplating what the exponential function is.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 2 on the exponential.
In this lesson, we'll introduce the principal hero of our story, the exponential function, and dive deeper into its definition and the implications thereof. We'll also see how Euler's formula entwines the exponential function with our principal supporting actors, the basic trigonometric functions.
We begin this lecture, and indeed the course, with the question, what is e to the x, the exponential function? Well, of course, it's a function. Hence, we can plot the graph of this function and consider what the output, e to the x, looks like for various inputs, x. But how do we compute some of these outputs, let's say for an irrational input, like pi? How would we even make sense of exponentiating an imaginary or a complex number? Is it possible to give meaning or sense to exponentiating an operator, like the derivative, or more unusual objects that you may have seen, such as matrices? Well, we won't answer all those questions today, but let's recall a few facts about the exponential function. Certain algebraic properties are manifest and well known to us. From your prior exposure to calculus, you should have seen some differential and integral properties. E to the x is that remarkable function that is its own derivative, and thus it is its own integral up to the constant of integration. There's one other fact that we need to move forward, and that is Euler's formula that tells us something about exponentiating a complex input, namely e to the ix is cosine of x plus I times sine of x. None of these properties, however, tell us what e to the x really means. We therefore move to the definition for the purposes of this course. This is what e to the x is and means. We define e to the x as 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the fourth plus 1 over 120 times x to the fifth, and this keeps on going and going. Where do these numbers come from? What do they mean? Well, another way to write this is using factorial notation. That e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. All the way down the line. One never stops. This sum keeps going forever and ever. Now recall that k factorial for a positive integer k is defined to be k times k minus 1 times k minus 2, all the way down until you get to 3 times 2 times 1. That gives the sequence of numbers that we saw at the beginning. Recall also that by convention, and for very good reasons, 0 factorial is defined to be 1. Thus, we could write our definition for e to the x using summation notation, as the sum k goes from 0 to infinity of x to the k divided by k factorial. This is a formula that you are going to want to memorize, as we will be using it throughout this course. Well, definitions may be nice, but what do we do with it? How do we deal with this statement? How do we even make sense of this infinite sum? Well, certainly for specific values of x, say x equal to 1, we could try to compute what e to the 1 would be as 1 plus 1 plus 1/2 plus 1/6 plus 1/24, etc. It seems as though this converges to the familiar decimal expansion for e that we know. In general, the principle that you should follow in trying to understand statements such as the definition of e to the x is to pretend that this is a long polynomial, a polynomial of unbounded degree. Now, polynomials are wonderful objects to work with, very simple from the point of view of differential and integral calculus. Recall that when it comes to differentiation, the derivative of x to the k is k times x to the k minus 1. Likewise, the integral of x to the k is x to the k plus 1 over k plus 1. Don't forget the arbitrary constant, and don't forget that something unusual happens when k is equal to -1. Both of these properties should be familiar from your previous exposure to calculus. Given these facts about polynomials, let's see what we can observe about e to the x. For example, if we tried to differentiate e to the x by using our definition, then what would we obtain? Well, thinking of e to the x as a long polynomial in x allows us to apply what we already know. For example, what is the derivative of 1? Well, that's clearly 0. The derivative of x is clearly 1. What is the derivative of 1 over 2 factorial times x squared? Well, it's 1 over 2 factorial times the derivative of x squared, which is 2x. We can continue on down the line, taking the derivative of x cubed to be 3x squared, etc., following the constants as we go. Now, a little bit of simplification tells us that the 2x divided by 2 factorial gives us simply x. The 3x squared divided by 3 factorial gives us simply x squared over 2 factorial. This pattern continues, since k divided by k factorial is 1 over quantity k minus 1 factorial. And what do we observe? We observe that we obtain the definition of e to the x by simply following what seemed to be the obvious thing to do. Will that work if we try to integrate as well? Let's see. If we try to integrate our definition of e to the x, 1 plus x squared over 2, etc., what will we get? Well, the integral of 1 gives us x. The integral of x gives us 1/2 x squared. If we have a 1 over 2 factorial times the integral of x squared, that's 1/3 x cubed. I'll let you follow this pattern all the way down the line and see that with a little bit of simplification, we wind up getting not quite e to the x. It appears as though we're missing the first term. We are missing the 1 out in front. So we've obtained e to the x minus 1. That's not quite the way I remember the integral of e to the x going. However, we have forgotten, as one often does, the arbitrary constant out in front. We can absorb that negative 1 into the arbitrary constant, and what we have obtained is, up to a constant, e to the x. That bodes well. Let's see what else we can do. Recall Euler's formula that tells us something about exponentiating I times x in terms of cosines and sines. What happens if we apply our definition of the exponential in this case? If we want to take e to the I times x, well, this is 1 plus I times x, plus 1 over 2 factorial times quantity ix squared, that is, I squared times x squared, etc., etc. There are a lot of terms here. Then it appears as though there are some simplifications that we could do. Recall that by definition, I squared, the square root of negative 1 squared, must be negative 1. Therefore, if we look at I cubed, we have to get negative I. And I to the 4th, being I squared squared, must be equal to 1. Therefore, we have a cyclic pattern in our powers of I that allows us to simplify this expression as 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the 4th over 4 factorial, etc. You can see the pluses and the minuses coming in alternating pairs, and the real versus imaginary terms alternating with each term. Now, if we were to do what we do when we work with complex numbers and collect all of the real terms into one part and all of the imaginary terms into the other, then what would we obtain? Well, the real portion of this expression is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc., with the signs alternating and with even powers of x. From Euler's formula, that must be the cosine of x. Likewise, the sine of x must be the imaginary portion of this expression, that is, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc., with odd powers and alternating signs. Our conclusion from this rather simplistic manipulation is that we now have alternate expressions for certain trigonometric functions. The cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. In summation notation, we could use a wonderful little trick to express this compactly as the sum, k goes from 0 to infinity, of negative 1 to the k times x to the 2k over quantity 2k factorial. That builds in the alternating signs and the even powers. Likewise, for sine of x, we can write this in a summation notation with a similar idea as the sum, k goes from 0 to infinity, of negative 1 to the k times x to the 2k plus 1 over quantity 2k plus 1 factorial. This gives us the odd powers of x. Now you may recall that the trigonometric functions have some very nice properties with respect to calculus. For example, you may remember something about the derivative of sine of x. Let's see what happens when we take our newly derived expression and differentiate it as if it were a long polynomial. The derivative of x is 1. The derivative of x cubed is 3x squared. We must divide this by 3 factorial. The derivative of x to the 5th and x to the 7th follow the familiar pattern. With a little bit of cancellation of the coefficients, what do we see? Well, we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. This is an expression that we have very recently seen. This is our derived expression for the cosine of x. And you may recall that the derivative of sine is cosine. But without any complicated proof, we've derived this expression very simply by pretending that everything in sight is a long polynomial. You could write this out in terms of summation notation. It looks a bit complicated, but it's a wonderfully convenient and compact way to perform this derivation. I'll leave it to you to check that you can do the same thing with the derivative of cosine of x, obtaining minus sine of x.
We now have new interpretations for the exponential function, as well as for sine and cosine. Don't panic if these feel unfamiliar. Take a look at the bonus lecture to see a more concrete perspective and to hear a few words of comfort. Be sure to take a look at that before moving on to our next lesson, where we introduce a series perspective for a broader array of functions.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 2, Bonus Material. In our main lesson, we saw a definition for e to the x in terms of a series. And from that, and a little bit of help from Euler's formula, we derived expressions for sine of x and for cosine of x. These can seem a little mysterious and difficult to work with at first, but if you think of these as long polynomials, polynomials of unbounded degree, it can make it easier both to work with them and to understand what these series mean. Let's consider the case of e to the x and see what happens when we cut off the series at some finite polynomial term, since polynomials are so easy to work with. If we stop after the first term, well, it's a bit too simple to conclude much. But if we keep going, looking at 1 plus x, or 1 plus x squared over 2 factorial, or continuing to include the cubic term as well, then we see that we're getting closer and closer to what the graph of e to the x looks like, especially if we zoom in very, very close to what's happening near the origin. Does the same thing work with the other series that we've looked at? Well, let's consider cosine of x. We know that the terms in the series expansion go like 1, and then 1 minus x squared over 2, and then 1 minus x squared over 2 plus x to the 4th over 4 factorial. And what we see is that we're getting closer and closer to what cosine is doing. The more terms that we add in this series, the better an approximation to cosine we obtain. It will come as no surprise to you that the same thing is true of sine, that when we look at the linear term, and then the cubic term, and then the 5th order term, that, although we're not getting exactly sine, we're getting something that is closer and closer. And this will keep on going. The more terms that we add, the better these polynomial approximations become to the true function. At this point, a few remarks are in order. First of all, these finite polynomial approximations work best near 0. If you want to approximate e to the x when x is very, very large, then you're going to need quite a few terms in order to get a good approximation. Now that's okay. E to the x really is this infinite series, but it's precisely because you include all of the terms. And second of all, sometimes you will see the term Maclaurin series used to apply to infinite series of this form. I choose to use the notation Taylor series exclusively, and in a few lessons we'll see exactly what type of Taylor series we're talking about when we write out things in this form. Lastly, and most importantly, at this point in the course, you may be ready to press the panic button. We have begun with material that is usually reserved for the end of a second semester calculus course. Relax. Don't panic. You'll see in just a few short lessons what the payoff is for beginning a calculus course with infinite series. Stick with it, learn the mechanics, and know that a deeper understanding is coming. This is not an easy course, and it's a long one. We have a lot of time left together. Don't panic. Work at it, and you'll make it to the end with a deeper understanding of calculus. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 3 on Taylor series.
In this lesson, we'll harness our understanding of e to the x as a series and extend this perspective to a wider world of functions. This will be done through the key tool of Chapter 1, that of the Taylor series of a function.
In our last lesson, we began with the definition of e to the x as something like a long polynomial, and from that, and a little bit of help from Euler's formula, we observed similar formulae or expressions for the basic trigonometric functions, sine and cosine. Expressions of this form we are going to call series, and we will be working with them throughout this course. The question arises, Are there other similar expressions for different functions besides these basic three? The answer is an emphatic yes. We're going to work under the assumption that every reasonable function can be expressed in the form of a series as a constant plus some other constant times x plus a third constant times x squared, etc., for some collection of constants. Now, of course, strictly speaking, this is not true. We need to be careful about what we mean by every and reasonable. For the moment, let's pretend that this is true and see where it gets us. We are first led to the question, how do we figure out or compute these coefficients? The following definition is critical. The Taylor series of a function f at an input 0 is the following series: f at 0 plus the derivative at 0 times x plus 1 over 2 factorial times the second derivative at 0 times x squared, etc. That is, the kth coefficient is equal to the kth derivative of f evaluated at the input 0 and then divided by k factorial. This is a most important definition. And for all intents and purposes, at this point in the course, remarkably, this series returns the value of f at x. Let's see how this plays out in an example that we already know. Starting with our definition of the Taylor series, let's apply it to the function e to the x. In order to compute this, we're going to need to know the derivatives of e to the x, and we're going to have to evaluate them at x equals 0. But since we know that the derivative of e to the x is e to the x, all of these derivatives evaluate to 1. Therefore, when we substitute these values into our formula for the Taylor series, we obtain the familiar series for e to the x. This definition, at least, works in this one context. Let's continue. Let's look at another function for which we know a series expression, that of sine of x. Recall how the derivative of sine goes. That gives you cosine. The derivative of cosine is minus sine. The derivative of minus sine is minus cosine, and then the derivative of minus cosine is sine. Once again, evaluating all of these at an input of 0 gives us alternating forms of 0 and non-zero terms, with the non-zero terms having alternating signs. Therefore, we can substitute in these derivatives, obtaining 0, 1, 0, negative 1, and repeating in blocks of 4. When we write out the resulting Taylor series, we see, once again, the familiar form x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. This is the expression for sine of x. It seems clear that this ought to work in other contexts as well, but let's just check it. For example, if we work with cosine of x, then, well, the derivatives of cosine follow the same pattern as before. Evaluating those to 0 gives us the same numbers as before. Why do we not get the same series? Well, because when we evaluate these derivatives, the sequence of numbers is shifted. F at 0, that is cosine of 0, is 1. The derivative at 0 is 0. Negative 1, 0, 1, and the pattern continues. When we simplify this expression, we see that all of the odd degree terms have 0 coefficients, leaving us with only the even degree terms in this series, and with the now familiar alternating signs, giving us our familiar expression for cosine of x. And so, it seems clear that we ought to be able to apply this method to other functions as well. Let us do so with another function that is at least reasonably simple. What would a very simple function be? Well, let's take a polynomial. In this case, x cubed plus 2x squared minus x plus 5. I know that we can differentiate this with ease. If we evaluate this function at 0, we obtain the first term in the series, namely 5. If we take the first derivative of this function, what do we get? Well, 3x squared plus 4x minus 1. Evaluating this at 0 gives us what? Well, that gives us negative 1. Therefore, the next term in the series expansion is negative 1 times x. Continuing, if we take the second derivative of this function, we will obtain 6x plus 4. Evaluating this at 0 gives us simply 4. Therefore, the next term in the Taylor series is 1 over 2 factorial times 4 times x squared. The third derivative of this function is very simple. It is exactly 6, independent of where we evaluate it. Therefore, the next term in the Taylor series is 1 over 3 factorial times 6 times x cubed. What happens when we take higher and higher derivatives? Well, the derivative of a constant is 0. Thus, all of the higher derivatives vanish, and all further terms in the Taylor series evaluate to 0. So we can drop them out without consequence. Rewriting, using a bit of simplification, gives us the Taylor series for this function as 5 minus x plus 2x squared plus x cubed. Let us take a look at our work. Do we believe what we have done? Well, of course, this is exactly the same function that we started off with. We've merely written the terms in ascending order of degree. This seems like a trivial example, but it is actually very crucial. You must remember that polynomials have themselves as the Taylor series. Polynomials have polynomial Taylor series. This is going to connect to some very deep properties concerning polynomial approximation. Our strategy, therefore, for working with functions is to think of Taylor expansion not as a function itself, but as something like an operator, as something that takes as its input a function and returns as its output something that is in the form of a long polynomial, or better, a series. Why do we want to do this? Well, series, thought of as long polynomials, are very simple to work with, whereas some functions can be obtuse, very difficult, maybe even unknown in a specific form. Taylor expansion helps us to convert such objects into an easier to work with form. Indeed, some functions really can't be defined well except as a Taylor series. Here's an example that I'll bet you've never seen before, though it's a famous function. This is the Bessel function, J0, that is most easily defined in terms of its Taylor series as the sum, k goes from 0 to infinity, negative 1 to the k, times x to the 2k over 2 to the 2k times k factorial quantity squared. That's a bit of a mouthful. We could write that out, and we would get something that it doesn't look too bad. There are a lot of complexities in the coefficients there. How might we understand this function? Well, let's see. The general form of it is reminiscent of the expression for cosine that we have derived, in that it has alternating signs and only even terms. But notice that the denominator of the coefficients is growing very rapidly, much more rapidly than k factorial or even 2k quantity factorial. We might therefore anticipate that the graph of this function looks something like a cosine wave, but with a decreasing amplitude as a function of x. Have you ever seen such a function before? Maybe you have. If you've ever taken a chain or rope and rotated it about a vertical axis, if it winds up in equilibrium, the shape that you will get is related to this Bessel function. If you drop a pebble in some water in a round tank or an open pond, the rippling effect of the waves is going to be very closely related to such a Bessel function. These are not too unusual, even in everyday occurrences. In fact, for a chain or a rope that is rotated in equilibrium, we can describe the displacement away from the vertical axis, r, as follows. This r is proportional to the Bessel function j0, evaluated at 2 omega over the square root of g times the square root of x. Here, omega is the angular frequency, or how fast you're spinning that rope. G is a gravitation constant, and x, most importantly, is the distance not from the top of the rope, but from the bottom of the rope. Now, you don't need to remember this formula. You don't need to know how it's derived. What we are going to look at is what happens when we substitute these values into our Taylor series for the Bessel function. One of the things that we can conclude from this Taylor series is that if x is reasonably small, if you're near the bottom of the rope, small enough that we can ignore some of the quadratic and higher order terms, then what's left over looks like a linear expression in x. R is proportional to 1 minus omega squared over g times x. That tells you something about the slope at the end of the rope, namely that this free end is swinging with a slope that is proportional not to omega, the angular frequency, but to omega squared. The faster you spin it, the more the slope changes. And we can say exactly what rate that change is. It's quadratic. You can try this at home with a piece of heavy rope or chain.
This lesson has given us a new definition, that of Taylor series, as well as a new perspective, the idea that expanding out a function into a long polynomial or series is advantageous. Next time, we'll consider the question of how one can effectively compute these Taylor series.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 4 on computing Taylor series.
We now have in hand the definition of the Taylor series, but the question remains, what is the best way to compute them? In this lesson, we'll cover some methods for clean and quick computations of Taylor series. In doing so, we'll see that this leads us to some new and interesting functions.
Recall the definition of a Taylor series. If you want to compute one of these, well, you may have to take a lot of derivatives, but that's not your only choice. There are a few other methods as well, including substitution and combination. Let's begin with an example that displays a substitution method. Consider the function 1 over x times sine of x squared. Computing the Taylor series for this might be a lot of work, having to differentiate this is not entirely trivial. However, we do know what sine of x is in terms of its Taylor series. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. If instead of using sine of x, we use sine of x squared, plugging in x squared into the Taylor series for sine of x, and then multiplying that by 1 over x, well, we obtain something that is going to work. A little bit of simplification gives x minus x to the 5th over 3 factorial plus x to the 9th over 5 factorial, etc. Another method for obtaining the same answer would be to take the full summation as k goes from 0 to infinity of negative 1 to the k times x squared to the 2k plus 1 over 2k plus 1 quantity factorial. By adding up the coefficients of the x term properly, we can, in fact, obtain the full Taylor series for this function as sum k goes from 0 to infinity, negative 1 to the k, x to the 4k plus 1 over quantity 2k plus 1 factorial. That means, in effect, that we have all of the derivatives of this function evaluated at 0 in one simple computation. There are other methods as well involving a combination of like terms. Consider the example of cosine squared of x. We know the Taylor series for cosine of x. It is the familiar 1 minus x squared over 2 factorial, etc. We can square that and then evaluate the product. How would we do so? If we consider these as very long polynomials, then we could apply what we know from polynomial multiplication. The lowest order term is equal to 1, that is 1 times 1. The next order term consists of 1 times negative x squared over 2 factorial plus negative x squared over 2 factorial times 1. The next order terms are of fourth order and consist of x squared over 2 factorial quantity squared. But there are a few others as well. There is an x to the 4th over 4 factorial term and another x to the 4th over 4 factorial term. All of the other terms are going to be of higher order. One could continue multiplying, although the multiplications would become a bit tedious. And now one must simplify these terms. With a little bit of work, it's easy to get the low order terms and to get 1 minus x squared plus x to the 4th over 3 minus x to the 6th times 2/45, etc. If you want more terms, you're going to have to do a bit more work. One thing that you can note, however, is that this must be 1 minus sine squared of x. And so from this, we obtain the Taylor series for sine squared of x as well. With these tools in hand, let us consider a new class of functions. These are the hyperbolic trigs. The hyperbolic cosine of x, or cosh of x, is defined as e to the x plus e to the minus x over 2. The hyperbolic sine of x is defined as e to the x minus e to the minus x over 2. What do these functions look like? Well, they don't look anything like a sine or a cosine. They both grow very rapidly in x due to the exponentials in their definitions. Nevertheless, these are very important and useful functions. There are others as well, such as the hyperbolic tangent, or tanh of x. As you might guess, this is really sinh of x over cosh of x, that is, e to the x minus e to the minus x over e to the x plus e to the minus x. Now, some of the rules that you're familiar with from trigonometry hold in this hyperbolic setting, but with a bit of a twist. For example, cosh squared of x minus sinh squared of x is equal to 1. One can compare that with the familiar formula cosine squared plus sine squared equals 1. What does this formula mean? Well, we know the relationship between cosine, sine, and points on a unit circle. Namely, cosine is the x-coordinate, the sine is the y-coordinate of a point moving along that unit circle. In the hyperbolic trigonometric setting, the same is true, but for a hyperbola instead of for a circle. As you might suspect, there are also hyperbolic secant, cosecant, and cotangent functions. Let's investigate these hyperbolic trig functions from the point of view of Taylor series. For example, if we consider the hyperbolic cosine of x as 1/2 e to the x plus 1/2 e to the minus x, then it's clear how to compute the Taylor series. Instead of trying to take derivatives, we'll simply substitute in the known series for e to the x, multiply by 1/2, and then add to it 1/2 times the series for e to the minus x, which, of course, is the Taylor series for e to the x with minus x substituted in, leaving negative signs at the odd powers of x. By combining terms according to degree, we see that all of the odd degree terms cancel, and we are left with only the even degree terms, the same as in the expansion of e to the x, 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. If we wish to write this out in summation notation, it would be the sum k goes from 0 to infinity of x to the 2k over 2k quantity factorial. Notice that just like the Taylor series for cosine of x, cosh of x consists of the even powers, but with no alternating sign. That is another relationship between the trigonometric and the hyperbolic trigonometric functions. Does the same hold for the hyperbolic sine? Well, let's investigate and see. Following the same method as before, we'll use the Taylor series for e to the x, and then the Taylor series for e to the minus x. But now, instead of adding these two terms together, we are going to subtract the latter from the former. This leads to a cancellation of all the even-powered terms. And distributing the minus sign through and adding, we obtain all of the odd degree terms in the Taylor series for e to the x. Thus, the sum k goes from 0 to infinity of x to the 2k plus 1 over 2k plus 1 quantity factorial, just like sine. We can continue our exploration of these functions by proceeding as if the Taylor series are like long polynomials. Hence, computing things like integrals or derivatives can be done term by term. Let's consider what the derivative of the hyperbolic sine of x would be. Well, we can differentiate the terms of the Taylor series. Since the derivative of x to the 2k plus 1 equals 2k plus 1 times x to the 2k, we can see by dividing by 2k plus 1 quantity factorial and summing as k goes from 0 to infinity that the derivative is the sum. K goes from 0 to infinity of x to the 2k over 2k quantity factorial. That is simply the hyperbolic cosine of x. in similarity to what happens with trig functions. The derivative of sinh is cosh. Likewise, what is the derivative of cosh of x? If we differentiate term by term, we can see that the derivative of x to the 2k is 2k times x to the 2k minus 1. Now we have to perform a shift in the index here in order to avoid problems with what happens when k equals 0. Reindexing properly gives us the sum. K goes from 0 to infinity of x to the 2k plus 1 over 2k plus 1 quantity factorial. That is the hyperbolic sine of x. And so we see that the hyperbolic trig functions are very nice. The derivative of sinh is cosh. The derivative of cosh is sinh. And this becomes clear from the Taylor series. Now, we're used to writing out the Taylor series term by term. Of course, since there are infinitely many, we can't write them all. We typically use a plus dot 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 or an ellipsis to connote what happens in the tail of the series. But there's another terminology that we will begin using, that of HOT, or higher order terms. This is an informal way of saying etc., and it can be a bit helpful. For example, you might say that cosine of x is 1 minus x squared over 2 plus higher order terms. We could say that sine of x is x plus higher order terms, or x minus x cubed over 3 factorial plus HOT. We could stop whenever we feel like. That's a convenient thing to do when performing computations on Taylor series. We'll use a more formal bookkeeping mechanism soon. Let's look at this in the context of a simple example. 1 minus 2x times e to the sine of x squared. We'll begin with the Taylor series for sine of x squared, which is simply x squared minus x to the 6th over 6 plus higher order terms. What happens when we exponentiate this? We use the Taylor series for e to the x. 1 plus our quantity above plus 1/2 times that quantity squared plus 1/6 times that quantity cubed, etc. Notice that I'm using plus higher order terms liberally in order to ignore things that aren't going to matter for the first few terms. To simplify this, we go degree by degree. The constant term is 1. There's only one quadratic term, namely x squared. Are there any fourth order terms? Well, yes, there is. 1/2 times x to the 4th. In the 6th degree terms, there are 2 of them, but notice that the coefficients balance each other out. And so the coefficient of the 6th order term is 0. We are left with a Taylor series of 1 plus x squared plus x to the 4th over 2 plus higher order terms. Now, to get the Taylor series for our original function f, we simply take 1 and subtract 2x times the quantity obtained above. I'll let you show with a little simplification that this is 1 minus 2x minus 2x cubed minus x to the 5th plus higher order terms. If you want more terms, you can get them. It will take more work.
We've now learned not only what Taylor series are, but how to compute them quickly and cleanly. Along the way, we've been introduced to 2 new characters in our story, the hyperbolic sine and cosine. In our next lesson, we're going to consider what happens when things don't work out so well. We'll deal with issues of convergence.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 5 on convergence.
Every epic adventure involves facing some sort of adversity. It's time that we confronted a challenge. Every series involves adding together an infinite number of terms. This is dangerous. In this lesson, we'll confront some of the technicalities associated with adding up an infinite number of terms. We'll find that along the way, we encounter series that are not only novel, but extremely useful.
There is clearly a problem with the principle that every function has a nice Taylor series about 0. It's simply not true. If we look at a function such as log of x, then of course this function is not even defined at x equals 0. There's no way that this can be true. One of the reasons behind this is that polynomials are simply too nice or simple to capture all of the complexities of functions that we see. Another problem is it is dangerous to add together an infinite number of terms. One must be careful. Let's look at an example where adding together an infinite number of terms can lead to something good. Consider the sum 1 plus 1/2 plus 1/2 squared plus 1/2 cubed, etc. The sum, k goes from 0 to infinity, of 1/2 to the k. As you may be able to guess from geometry, if nothing else, this sum converges, and converges quite simply to the number 2. This is an example of something called a geometric series. You may have seen it before. The more general version of the geometric series is 1 plus x squared plus x cubed, etc. The sum, k goes from 0 to infinity, of x to the k. The geometric series says that this equals 1 over 1 minus x. So that, for example, if x equals 1/2, this sum converges to 2. How would you prove something like this, even for values of x not equal to 1/2? Well, let's see. Let us take this infinite sum and call it y. If we multiply this by x, then we obtain x plus x squared plus x cubed, etc. If we were to subtract that from our original series, y, then we see that everything cancels except for the first term, so that y minus x times y equals 1. Factoring and solving for y gives that y equals 1 over 1 minus x. That is clear as far as an algebraic manipulation, but does this actually work? Does it make sense? What happens if we plug in x equals 1? Then we get 1 plus 1 plus 1 plus 1 plus 1. Clearly, that is not a finite number. And 1 over 1 minus 1 doesn't even make any sense. That is undefined. Well, this derivation only holds for values of x less than 1 in absolute value. Otherwise, this infinite series does not converge. Let's take a look at what happens at the other extreme. What if x equals minus 1? Is there really a problem here? Well, we would be asking for the sum 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. Maybe this does have a well-defined answer if we paired up the terms 1 minus 1 plus 1 minus 1. Then we would seem to get 0. What's wrong with that? Well, if you could do that, then why not pair the terms a bit differently and take 1 minus 0 minus 0 minus 0, so that the sum would be equal to 1. If you're not sure which of these is correct, perhaps the best thing to do is to take the average, split the difference, and declare it to be 1/2. This is, after all, what one would obtain by plugging in a value of -1 into the expression 1 over 1 minus x. Well, as you might guess, none of these is correct. This series does not converge at a value of x equals -1, or for any value of x that is not less than 1 in absolute value. The moral of the story is that this and other Taylor series possess a convergence domain on which the series is well defined and well behaved. Now, for many of the Taylor series that we've encountered thus far, the domain of convergence is the entire real line. For the exponential function, sine, cosine, hyperbolic sine, hyperbolic cosine, there are no convergence issues. It is for series like the geometric series that we have to be more careful. Now, within the domain of convergence, you can manipulate the series at will. You can rearrange the terms, differentiate term by term, integrate, recombine, whatever you wish. There are no problems as long as you are within the interior of that domain of convergence. You must be very careful about what happens near the borders. We'll talk more about that in Chapter 5. For the moment, I want to focus on what we can do. Let's take a look at another example. Compute the Taylor series of not log of x, but log of quantity 1 plus x. Maybe this will be not so bad, since for small values of x, this function is well defined. We could start taking derivatives of this function, but manipulating a known series is going to be a bit easier. One of the things that you may recall is that the log of 1 plus x is equal to the integral of 1 over 1 plus x dx. If you remember that, great. If you don't worry about it. Accept it as a given. And let's move on from there. What could we do with that integrand, 1 over 1 plus x? That is really the geometric series evaluated at negative x. And so we could integrate the sum, k goes from 0 to infinity, of negative x to the k with respect to x. By rearranging the terms, a thing that we are allowed to do as long as we are within the convergence domain, and pulling out the -1 to the k, then we get the sum, as k goes from 0 to infinity, of -1 to the k times the integral of x to the k, that is, x to the k plus 1, or k plus 1. If we add an arbitrary constant out in front, well, that's actually not going to be so bad. And why? When x equals 0, we obtain the log of 1, which is 0. So forget that constant. And now we have an answer with a bit of reindexing. As the sum, k goes from 1 to infinity, of -1 to the k plus 1 times x to the k over k. That is perhaps more easily remembered as x minus x squared over 2 plus x cubed over 3, etc. Notice there are no factorials here. This is x to the k over k. Now, are there any problems with this? Well, since we used the geometric series in this derivation, we must be careful to remain within the convergence domain for this. X must be less than 1 in absolute value. This fits well with the principle that Taylor polynomials approximate well only on the convergence domain. If we look at the terms of this series as an approximation to log of 1 plus x, we get, increasingly, something that seems to fit what the curve is doing, but only on the domain of convergence as x goes from -1 to 1. That is, we're looking at values of log from 0 to 2. Outside of this region, these polynomial curves do not become better and better approximations. They, in fact, become worse and worse. Let us consider another example, this time the arctan function. One of the things that you may recall is that arctan has as its derivative 1 over 1 plus x squared. So we can integrate this to obtain arctan. You will notice also that 1 over 1 plus x squared can be represented as the geometric series of negative x squared, so that we can integrate the sum of negative x squared to the k, as k goes from 0 to infinity. Again, by rearranging terms, doing a little bit of work here, we see that we get the sum, k goes from 0 to infinity, of -1 to the k times the integral of x to the 2k, that is, x to the 2k plus 1 over 2k plus 1. We have to deal with the constant of integration, but again, since arctan of 0 equals 0, it is irrelevant. We therefore obtain the Taylor series x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, etc. Once again, no factorials in those denominators. And once again, it is important that x remain less than 1 in absolute value in order for this series to converge, because we used the geometric series as its basis. There is one last series that will be very helpful to us. This is the binomial series. It is the Taylor series for 1 plus x to the alpha, where alpha is a constant. This series is 1 plus alpha x plus 1 over 2 factorial times alpha minus 1 times x squared. Well, there are a lot of other terms here. Let me say simply that the kth order term is alpha choose k times x to the k, where by alpha choose k, I mean a binomial notation. This is the number alpha times alpha minus 1 times alpha minus 2 all the way down to alpha minus k plus 1. Take that product and divide by k factorial. For example, if alpha equals 2, then what does the binomial series give you? 1 plus alpha times x plus 1/2 alpha times alpha minus 1 times x squared. That simplifies to x squared. All other terms involve an alpha minus 2. Hence, the coefficients are 0. And we obtain, of course, what the Taylor series for this polynomial must be. When alpha equals -1, we're really looking at a variation of the geometric series for 1 over 1 plus x. This, however, holds for all values of alpha. For example, if we take alpha equal to 1/2, so that we're looking at the square root of 1 plus x, then one can evaluate these binomial coefficients and obtain a Taylor series for that. In this case, in particular, this is only going to remain valid for x less than 1 in absolute value. We now have a full collection of Taylor series. Many of these have domains of convergence that are infinite. E to the x, cosine and sine, and cosh and sinh. These are the nicest Taylor series that you're going to run into in this course. However, from this lesson, we have another collection of Taylor series that are guaranteed to converge only when x is less than 1 in absolute value. This is the geometric series, the series for log of 1 plus x, the series for arctan, and the binomial series. These, one has to be a bit careful with, but as long as you are within the domain of convergence, these are wonderful series.
The moral of this lesson is that so long as you are within the domain of convergence, you can do wonderful things. Check out the bonus material for this lecture for an additional example. In our next lesson, we'll consider what happens when you wish to focus your attention on some specific location, an expansion point.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 5, Bonus Material. In our lesson, we saw two important series that have convergence constraints. These are the geometric series for 1 over 1 minus x and the binomial series for 1 plus x to the alpha. Both of these are guaranteed to converge only when x is less than 1 in absolute value. Let's put these series to work in a problem in electrostatics. An electric dipole is a pair of equal and oppositely charged particles separated by a short distance. Now, this is a calculus class, not a physics class. Don't worry, you're not going to need to know this for the exam, but let's learn a little bit, have some fun with it. The electrostatic potential gives the potential energy of this dipole, this pair of charges, as a sum of point charge potentials. And what do I mean by that? Well, each charge has a potential energy associated to it. The pair of them together yields a potential energy that depends on your position. So let's say that you're at some location away from the dipole. You want to know what is the electrostatic potential. It's given by the following formula. V is equal to kq over d plus minus kq over d minus. What does that mean? Well, k is a constant, the Coulomb constant. Q is the amount of charge on each element of this dipole. And d plus and d minus are the distances, respectively, to the positive and the negative charge in the dipole. All right, that's the physics that we need. Let's do some math. Let's compute what this electrostatic potential V is in the case where you are standing at a distance d away from the positive charge and where d is much greater than r, the separation distance between the two charges in your dipole. Now, I'm going to assume that we are orthogonal to the dipole. That is, we're at distance d from the positive charge, but perpendicular to the orientation of the dipole. That means that the distance to the negative charge is, by Pythagoras' theorem, the square root of d squared plus r squared. So that in computing v, we get kq over d, the positive charge distance, minus kq over square root of d squared plus r squared. We could stop there, but let's simplify this as much as possible. If we factor out kq over d, then we get a 1 from the left term. From the right term, we get 1 over square root of quantity 1 plus r over d quantity squared. Well, at this point, we can try to expand that out using the binomial series. Recall, the binomial series is for something of the form 1 plus x to the alpha. In this case, alpha is negative 1/2. We're looking at 1 over the square root of something. And x is r over d quantity squared. Because the first two terms in the binomial series are 1 plus alpha x, we get the first two terms in the series applied here to be 1 minus 1/2 times r over d quantity squared. Simplifying, we see that the 1's cancel, and we're left with kq over d times 1/2 r over d quantity squared. Everything else is of higher order term in r squared over d squared. Let's remember that 1/2 r over d quantity squared. In fact, we'll set it over here, right next to the location, and consider what happens when we look a distance d away from that positive charge, but in a different direction. Instead of being orthogonal to the dipole, let's look parallel to it. Well, in this case, d plus remains the same. It is this distance, d. But now, d minus is a bit simpler looking. It is d plus r, the separation distance in the dipole. Now again, factoring out a kq over d, we get a term on the right-hand side that is of the form 1 over 1 plus r over d. We can expand this out using, if we like, the binomial series with alpha equal -1, or what that really is, the geometric series for 1 over 1 minus x, with x being equal to negative r over d. Writing out the first two terms of that series as well, we get 1 minus r over d. The 1's cancel, just as before, and we see that up to the leading order term, our electrostatic potential is kq over d times r over d. Now, notice how different that is from before. By using different series, we see that the leading order terms in the electrostatic potential differ depending on how you are oriented with respect to the dipole. Inline potential is much stronger than orthogonal. This is just one example of how we can use different series in order to get a handle on various physical phenomena by expanding, ignoring the higher order terms, and retaining the leading behavior. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 6 on expansion points.
We've seen that the Taylor series provides a good approximation to a function near zero. What happens if we wish to focus our attention at some other point? In this lesson, we'll consider changing the expansion point. This will lead us to a broader definition and interpretation of Taylor series.
As we have seen, Taylor expansion gives an excellent way to approximate a function for inputs near zero. However, in many applications, zero is not the most interesting input. I bet you can think of many examples of this besides finance and economics, where we care about non-zero values. What would be nice is a way to Taylor expand a function that works well for inputs that are not necessarily close to zero. There certainly is. This is an important definition. The Taylor series of f at x equals a is the sum k goes from 0 to infinity, the kth derivative of f evaluated at a, divided by k factorial times quantity x minus a to the k. This is not a polynomial in x, but rather a polynomial in the quantity x minus a, where the coefficient in front of each monomial term is the kth derivative of f evaluated at a, and then divided by k factorial. A little bit of terminology is in order. The constant term is called the 0th order term. Next comes the first order term, the second order term, the third order term, and so on. These correlate to the degree of the quantity x minus a. If we were to change things, perform the change of variables, defining h to be the quantity x minus a, then the above series would become a polynomial series in h. However, it would not be giving you f of h, but rather f of x, which is a plus h. This series in h is telling you that if you want to know values of f that are close to a, then you can substitute in a small value for h, and if you're looking for an approximation, you can ignore some of the higher order terms. Let's look at an example. Compute the Taylor series of log of x. Now we know that we cannot do that about x equals 0, so let us do it about a more natural value. Let's say about x equals 1. To compute this Taylor expansion, we're going to need to start taking some derivatives. If we look at the function log of x, the 0th order term is obtained by evaluating at x equals 1. And that gives us simply 0. The derivative of log of x, you may recall, is 1 over x. Evaluating that at x equals 1 gives us a coefficient of 1. Now, taking the derivative of 1 over x gives us minus x to the negative 2. We evaluate that and continue differentiating as we go, evaluating each term at x equals 1. After computing sufficiently many derivatives, you start to see a pattern. It requires a little bit of thinking and a particularly formal way of thinking called induction. But with a bit of effort, one can conclude that the kth derivative of log of x is negative 1 to the k plus 1 times k minus 1 factorial times x to the minus k. Evaluating that at x equals 1 gives us simply the coefficient negative 1 to the k plus 1 times k minus 1 factorial. Now, to get the full Taylor series, we need to divide this coefficient by k factorial. In so doing, we see a not too unfamiliar series for log of x as x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3, etc. The coefficient in front of the degree k term is negative 1 to the k plus 1 over k, and our summation goes from 1 to infinity. Indeed, if we let h be x minus 1, then we obtain the very familiar series log of 1 plus h equals sum k goes from 1 to infinity, negative 1 to the k plus 1, h to the k over k. We've seen that before with an x instead of an h, but it works the same. Do keep in mind that Taylor series are not guaranteed to converge everywhere. Indeed, if we look at the terms for log of x and take a finite Taylor polynomial, then the higher and higher degree terms only provide a reasonable approximation to log of x within the domain of convergence. We know from our last lesson that that domain is going to be for values of x between 0 and 2. Outside of that, these terms are providing worse and worse approximations to log of x. Now, what do we do if we want to approximate log of x outside of this domain? Well, you need to do a Taylor expansion about a different point, someplace close to where you want to approximate. It's a bit easy to get confused with all of the different notation associated with Taylor series, so let's review. One way to think about the Taylor expansion about x equals a is to write f of x as a series in the quantity x minus a. Another way to do it is to write it as a series in the quantity h, where h is equal to x minus a, in which case you're coming up with an approximation for f of a plus h. One way to think about this is that the more derivatives of f you know at a point a, the better an approximation you get at x, or at a plus h. This is a perspective that you're going to want to keep with you for the remainder of this course. The principle is that successive polynomial truncations of the Taylor series approximate increasingly well. We've seen that before. In this lesson, the point is that where you do the Taylor expansion matters. If you're expanding way over here and trying to get information about way over there, then you're going to need a lot of derivatives to do that. On the other hand, if you approximate about the correct expansion point, you might not need so many derivatives in order to get the job done. Let's look at an explicit example. What would it take to estimate the square root of 10? Well, we would have to look at the Taylor series of the function square root of x. If we expand that about a point x equals a, then I'll leave it to you that the first few derivatives work out to a Taylor series of root a plus 1 over 2 root a times quantity x minus a minus 1 over 8 times the square root of a cubed times quantity x minus a squared plus some higher order terms in x minus a. Well, to compute the square root of 10, what are we going to do? Let's say I expand about 1, because 1 is a simple value. I know the square root of 1, that is simply 1. That makes the coefficients of the Taylor expansion easy to compute. On the other hand, when I actually try to estimate the square root of 10 based on this, then I get 1 plus 1/2 times 9 minus 1/8 times 9 squared, or 81, plus higher order terms. How good of an approximation is that? Well, that gives me a value of negative 4.125. I know this is not the square root we're looking for. That is a bad approximation. So, what if we were to compute an expansion about x equals 9? Then, this is something for which I also know the square root. The square root of 9 is 3. The coefficients are easy to work with. And if I plug in a value of x equals 10 into this Taylor series, I get an approximation of 3 plus 1/6 minus 1 over 216. This gives an approximation of 3.1620, some other stuff. The true answer agrees with this up to the first 4 digits. The expansion point, in this case, certainly matters. Now, one thing to be cautious of is that if you're computing a Taylor series of a composition, you must expand about the correct values. If you have a function f composed with g, and you want to expand it about some input x, then you must expand g about x, but you must expand f, not about x, but about g of x. And it is that term in particular that causes problems. In an explicit example, we'll be able to see how this works. Compute the Taylor series of e to the cosine of x about x equals 0. Well, e to the cosine x is a composition. What do you do first? First, you take the cosine of x, then you exponentiate it. If we are to compute the Taylor series about x equals 0, then we must expand cosine about 0, but not e to the x. Cosine of x about 0 is very simple. This one we know. However, for the second term, the exponential, we must expand that about an input of 1, because that is what gets fed into it. Cosine of 0 is 1. Well, the Taylor series of e to the u about u equals 1 is easy to compute. There's nothing difficult there. However, what we must then do is substitute into it this series for cosine of x. That is, u is 1 minus x squared over 2 plus x to the 4th over 4 factorial plus higher order terms. That is a little bit too much algebra to fit on this slide, and so I'll leave you to do that. Though I might point out a little bit of help here, that this can be rewritten as e times e to the cosine of x minus 1. You'll find that to be a little bit easier to compute the Taylor series of.
This lesson marks the end of our introduction to Taylor series. But by no means does it mark the end of our use of Taylor series. In our next lesson, we will consider one of the primal objects of calculus, the notion of a limit, and we'll consider it using the understanding gained from Taylor series.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 7 on limits.
In many respects, calculus can be defined as the mathematics of limits. In this lesson, we'll review the concept and definition of a limit, consider a few examples, and see that one of the most effective tools for computing a limit involves Taylor series.
In your previous exposure to calculus, you have certainly seen limits. But what does it mean to say the limit as x approaches a of f of x equals L? Well, I'm sure you have an image in your head that as x gets closer and closer to a, f of x gets closer and closer to L. Perhaps you remember that it doesn't matter whether you approach from the left or from the right. Perhaps you remember that it doesn't matter what the actual value of the function is at x equals a. What matters is the limit. Well, this picture is the intuition behind a limit, but it is not the definition. The definition is another thing altogether. What is it? The limit of f of x as x goes to a equals L if and only if, for every epsilon greater than 0, there exists some delta greater than 0, such that whenever x not equal to a is within delta of a, then f of x is within epsilon of L. That is a bit of a mouthful, and a lot of students have difficulty with it. Why? Because as a logical statement, it is complex. As a grammatical statement, it is complex. How does one make sense of this? Well, A picture is not a bad way to go if we think of L as a target that we are trying to hit. Then we are allowed some tolerance on the output. This tolerance is in the form of an epsilon. You have to get within epsilon of L. Using your function, you can set the input to be as close to A as you like, but there's going to be some tolerance on the input, some degree of error that is bounded by delta. In order to have the limit of f of x as x approaches a equals L, then anything within the input tolerance has to hit the target within the output tolerance. This must be true no matter how small the output tolerance epsilon is. You can find some sufficiently small input tolerance to guarantee always striking within range of the limit. In the context of an actual function, f, one can visualize this delta epsilon definition as follows. You choose an output tolerance, epsilon. Then there must be some input tolerance, delta, so that any input within delta of A has an output within epsilon of L. Now, many students get confounded here, trying to find the optimal delta. It does not need to be optimal. You can choose something smaller. That is not a problem. The critical part of the definition is that as you change epsilon, you need to be able to update delta. If you make epsilon smaller still and decrease your level of acceptable error on the output, you need to find some amount of acceptable error on the input. And this has to continue for every possible non-zero value of epsilon. That is what captures what the limit is. This view of the definition is extendable to other contexts. Consider the limit as x goes to infinity of f of x. What does it mean for that to be equal to L? Well, we're going to think about infinity as something like an endpoint to the real line, modifying its topology so that it looks like a closed interval. Now, this is a dangerous thing to do if you don't know what you're doing, but let's think about it from the perspective of our interpretation of a limit. Given any output tolerance, epsilon, there must be some tolerance on the input that guarantees striking within epsilon of L. Now, how do we take a neighborhood of infinity? How do we talk about a tolerance on that input? Well, what it becomes in this context is some lower bound, m, so that whenever your input is greater than m, then your output is within epsilon of L. As before, this must be true no matter what epsilon you choose. If you make your tolerances on the output tighter and tighter, then we can make the tolerances on the input tighter and tighter. In this case, instead of talking about being within delta of infinity, since we're only looking at a one-sided limit, we can speak in terms of an explicit lower bound on x. The same intuition and picture holds. To be sure, not all limits exist, and not all functions well behaved. There are several ways in which things can go wrong. You could have a discontinuity at a function. The limit would not exist at that point. You could have what is called a blow-up. That is, the function goes to infinity as x gets closer and closer to a. Or, worse still, the limit can fail to exist because of an oscillation, where the function oscillates so badly that the limit at a does not exist. On the other hand, most of the time, you're not going to have to worry about this because most functions are continuous. We say that f is continuous at an input, a, if the limit as x goes to a of f of x exists and equals f at a. We say that f is continuous everywhere if this statement is true for all inputs a in the domain. Now, most of the functions that we're used to seeing are continuous functions, and one doesn't have to worry so much about limits in this case. There's a bit of a technicality. One has to be very explicit about which points are in the domain of the function. Some functions which look discontinuous may actually be continuous if the discontinuous looking point is not actually in the domain. If, however, the function is defined there, then the discontinuity presents itself. There are certain rules associated with limits that you may know by hand, even if you don't remember them. If the limit of f of x as x approaches a and the limit of g of x as x approaches a both exist, then the following rules are in effect. There's a summation rule that the limit of the sum of f plus g is, in fact, the sum of the limits. There is, likewise, a product rule that the limit of the product of f and g is, in fact, the product of the limits. There is, likewise, a quotient rule that the limit of f divided by g is the limit of f divided by the limit of g. Now, at this point, you've got to be a bit careful. If that denominator is 0, well then, this limit may not exist. There is likewise a chain rule or a composition rule that says the limit of f composed with g as x goes to a can be realized as f of the limit of g as x approaches a. And once again, this too has some conditions. F, in this case, needs to be continuous at the appropriate point in order for this to hold. Now, at this point, I think we're going to have a little quiz to test your knowledge of limits. What is the limit as x approaches 0 of sine of x over x? This is a quotient. Can we apply our quotient rule for limits? No, I'm afraid we cannot, because the denominator is going to 0, and so is the numerator. And 0 over 0 presents some difficulties. Now, I'll bet that most of you know the answer is 1. But why do you know this? Well, you may say, I remember this. This is something that I had to memorize when I took high school calculus. Very useful on exams. I just know it. Well, that's not a very satisfying answer, is it? Some of you may say, I wield the mighty sword of L'Hopital's rule, and I know that if I differentiate the top and the bottom, then I get 1. That's great, and I'm glad you remember L'Hopital's rule. But do you know why it works? Do you have a good reason for your belief in this rule? Well, if not, then let's take a method that we do trust, namely Taylor series. If we consider the limit as x goes to 0 of sine of x over x, we know what sine of x is. That's x minus x cubed over 3 factorial plus higher order terms. Now, thinking of this, as we do, as a long polynomial, what are we tempted to do? Well, I look at that and say, hey, we could factor out an x from the numerator and cancel that with the x in the denominator, yielding the limit as x goes to 0 of 1 minus x squared over 3 factorial plus higher order terms in x. Sending x to 0 gives us an answer of 1. The limit makes perfect sense. Likewise, you might recall that the limit as x goes to 0 of 1 minus cosine of x over x is, what was that? Oh well, I don't remember, but I do remember what cosine of x is. And I note that here the 1's cancel, and I'm left with the limit of x squared over 2 factorial minus x to the 4th over 4 factorial plus higher order terms. When I divide that by x, I get the limit of x over 2 factorial minus x cubed over 4 factorial plus higher order terms. There's no 0 over 0 ambiguity anymore. This limit is precisely 0. Now, one of the wonderful things about this Taylor series approach to limits is that it works even in cases where you might not have memorized the limit, and where the limit is indeed not so obvious. Let's look at the cube root of 1 plus 4x minus 1 over the 5th root of 1 plus 3x minus 1. It is clear that evaluating at 0 is not going to work. That yields 0 over 0. So what do we do? Well, rewriting this a little bit allows us to use the binomial series, with alpha equal 1/3 in the numerator and 1/5 in the denominator. Applying that gives us 1 plus 1/3 times 4x plus higher order terms. Subtract 1. In the denominator, 1 plus 1/5 times 3x plus higher order terms. Subtract 1. Those subtractions get rid of the constant terms. We're left with terms that all have an x in them. We factor that out, and then the leading order terms are 4/3 in the numerator and 3/5 in the denominator, yielding an answer of 20/9. That is beautiful.
There is a vast gulf between knowing how to compute something and knowing what that thing is. The question of evaluating or computing a limit is subtle, and it weaves its way throughout this course. In our next lesson, we're going to consider one of the primary tools for evaluating limits, that of L'Hopital's rule.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 8 on L'Hopital's rule.
Everyone who's had some exposure to calculus knows of L'Hopital's rule. Everyone who knows L'Hopital's rule loves L'Hopital's rule. But who understands why L'Hopital's rule works? By the end of this lesson, you will.
Recall that when faced with a tricky limit, L'Hopital's rule is a good method. For example, if we look at the limit as x goes to 0 of sine of x over x, or the limit as x goes to 0 of 1 minus cosine of x over x, you probably remember that the way to deal with these is to differentiate the numerator and the denominator. The derivative of sine is cosine. The derivative of x is 1. Taking that limit gives you the correct answer of 1. Likewise, in the second example, the derivatives of the numerator and denominator give sine of x and 1, respectively, leading to an answer of 0. But what does L'Hopital's rule really say? Well, remember the way that it is applied. You begin with a limit of the form of a quotient, say f of x over g of x. Then you try to evaluate the limit. If that works, then great, you're done. If that doesn't work, then L'Hopital's rule says to differentiate both the numerator and the denominator. Try to evaluate the limit again. If that works, great, you're done. If not, repeat until it does work. Now, the error that some students make is to begin differentiating as soon as they see a limit that looks like a quotient. That is a bad idea. It will fail in those cases. But the question is, why? Why does it work? Why, if it doesn't work the first time, do you keep trying until it does? Let us use the perspectives that we've worked with so far and Taylor expand the terms. If we have the limit as x goes to a of f of x over g of x, then expand both the numerator and the denominator about the input a. Now, in the context of L'Hopital's rule, let's consider the case where the limit of f is 0 and the limit of g is 0. That means that the 0th order terms both vanish. What do we see? Well, we see that we can factor the quantity x minus a from all remaining terms in the Taylor expansions in both the numerator and the denominator. These cancel. And now, when we try to evaluate at x equals a, we're left with the leading order terms. The constants are really the derivatives evaluated at a. Now, if those two were to vanish, then what would happen? Well, we see that once again we can factor out the quantity x minus a, cancel, and again we see that the leading order terms involve the second derivatives at a. Now you might wonder, what about the 1 over 2 factorial? Since it appears in both the numerator and the denominator, it doesn't matter. What really matters is the derivatives. Let's look at this in an example. Sometimes L'Hopital's rule is much easier to apply than a Taylor series. For example, if we take the limit as x goes to 0 of tangent of x over arcsine of x, well, I don't know the Taylor series for tangent and arcsine off the top of my head, and it might take a lot of work to figure that out. So let's apply L'Hopital's rule. If we try to differentiate, well, that's going to take a little bit of recollection. You may or may not remember that the derivative of tangent is the secant squared. You may or may not remember that the derivative of arcsine is 1 minus x squared to the negative 1/2 power. If you don't remember this, don't worry. We'll learn how to compute these in just a few short lessons. But for the moment, let's take it as a given. Using L'Hopital's rule, we get the limit as x goes to 0 of secant squared x over 1 minus x squared to the negative 1/2. Evaluating at 0 and remembering that secant of 0 is 1 gives us our answer of 1. That was simple. Let's look at another example, one for which L'Hopital's rule might not be the way to go. The limit as x goes to 0 of x squared log of cosine of x over sine squared of 3x squared. Whew, I do not want to try to compute the derivative of that. It's possible, but not profitable. However, I recall the Taylor expansions for cosine of x, for log of 1 plus something, and for sine of something. These are all very simple. We've done these before. Now, using the fact that the limit is as x goes to 0, and cosine of x about 0 is 1 minus x squared over 2 plus higher order terms, then substituting in for sine 3x squared and dropping all the higher order terms of sine, and then we have to square that. Ooh, this way is not so easy either. But it's not that bad. We're left with expanding log of 1 minus x squared over 2 plus higher order terms. That is in the form log of 1 plus z. The first term is z itself, in this case, negative 1/2 x squared. we'll forget about the higher order terms. Hopefully they won't matter. In the denominator, when we square 3x squared plus higher order terms, the first term is 9x to the fourth. Whew. And now we see that the leading order terms are of the same degree. We get negative 1/2 x to the fourth plus stuff over 9x to the fourth plus stuff. Factoring out an x to the fourth and canceling gives us an answer of negative 1/18. Now, not all tricky limits are in the form of 0 over 0. For example, the limit as x goes to 0 of 1 over sine squared x minus 1 over x squared. Evaluating looks like infinity minus infinity. That's not going to work. So let us put this over the common denominator of x squared times sine squared of x. The resulting numerator is x squared minus sine squared of x. And now we can apply L'Hopital's rule, or, in this case, Taylor expansion. If we Taylor expand, well, the only thing we need to worry about is sine squared of x, which is the Taylor series for sine of x, quantity squared. What we really want to do is compute the leading order term. So we're going to have a little bit of algebra to do. When we square x minus x cubed over 3 factorial plus higher order terms, what do we get? The first term is x squared. The second term is 2 times x cubed over 3 factorial. Now, what do we note here? We note that the x squareds cancel. Those second order terms and go away, and we're left with the next term, the fourth order term, as the leading order coefficient. Likewise, in the denominator, we see that the leading order term is simply x to the fourth. Thus, canceling the x to the fourths gives us leading order coefficients of 1/3 in the numerator and 1 in the denominator. Our answer is 1/3. Likewise, if we consider x times log of x and send x to 0, we're going to have to be a little careful. This is a one-sided limit, sending x to 0 from the right. Then what would this be? Well, x is going to 0. Log of x is going to minus infinity. 0 times minus infinity, that's not going to work. Once again, let us put this over a denominator. In this case, we'll move the x to the denominator and call it 1 over x, so that we have a ratio of two functions. In this case, log of x over x to the minus 1. Now, we're going to apply L'Hopital's rule. I'm a little nervous about Taylor expansions here, because both log of x and 1 over x don't seem to have good Taylor expansions at x equals 0. So, applying L'Hopital's rule gives us what? The derivative of log of x is 1 over x. The derivative of 1 over x is minus 1 over x squared. These simplify to minus x. And taking the limit as x goes to 0 from the right, we see that the answer is 0. Now, L'Hopital's rule can also help in evaluating limits at infinity. Consider the limit as x goes to infinity of log of x over square root of x. It's maybe not apparent what that limit is going to be. Log of x and square root of x both become infinite as x goes to infinity, but at what rate? Is there one that is bigger than the other? Well, let's apply L'Hopital's rule. This gives us the limit as x goes to infinity of what? The derivative of log of x is 1 over x. The derivative of x to the 1/2 is 1/2 x to the minus 1/2. This simplifies to twice x to the minus 1/2. As x goes to infinity, this clearly goes to 0. Well, that's the answer, but what does that really mean? A log of x is going to infinity, square root of x is going to infinity, their ratio is going to 0. What that really means is that the square root of x dominates the log of x. It grows much faster than the logarithm does. While it's true that L'Hopital's rule tends to be helpful in evaluating limits at infinity, it's not universally helpful. Sometimes you have to think. Consider the limit, as x goes to infinity, of the hyperbolic tangent of x. That is, by definition, the limit of the hyperbolic sine over the hyperbolic cosine. Let's apply L'Hopital's rule. Well, this is easy. What's the derivative of sinh? It's cosh. What's the derivative of cosh? It's sinh. And so we get the limit as x goes to infinity of the hyperbolic cotangent of x. I don't know what that is, so let's apply L'Hopital's rule again. The derivative of sinh is cosh, and of cosh is sinh. And unfortunately, we're stuck in a loop, and we'll never get anywhere. But using our collective head, we know the definition for the hyperbolic tangent. What we really care about is the ratio of e to the x minus e to the minus x over e to the x plus e to the minus x. Now let's think about that. Those first terms are big. E to the x gets large very quickly as x goes to infinity, and e to the minus x gets very, very small. Let's ignore it. What would we get? Well, I think you could argue that the limit ought to be 1. How can we make that a little more precise? If we factor out an e to the x, we're left with 1 minus something going to 0 in the numerator and 1 plus something going to 0 in the denominator. Canceling gives us easily this limit. This is a useful way to argue. Consider the limit of x times log of x over log the hyperbolic cosine as x goes to infinity. I'm going to let you do the work to apply L'Hopital's rule and see what we get. What we're going to get winds up looking a little complicated. Fortunately, there's a hyperbolic tangent involved, which allows us to use our previous result to say that the numerator is going to infinity while the denominator goes to 1. What I want you to do is think about how that answer of infinity could be obtained in your head without L'Hopital's rule. Consider the hyperbolic cosine of x. That's really e to the x plus something small, up to a constant of 1/2. Now, if we take the natural log of that, that should look something like x. Not exactly, but it should grow linearly. And so I would argue that x times log of x divided by something that grows like x should give us an infinite limit. That's a foreshadowing of what is to come, where we want to have a language for discussing or controlling growth of functions. This is called Big O, and it's a beautiful language.
L'Hopital's rule, together with Taylor series, form a wonderful set of tools for evaluating limits. In our next lesson, we'll put these tools to use in studying asymptotics or growth rates of functions. Along the way, we'll augment our tools with one more device, that of Big O.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 9 on orders of growth.
In this lesson, we'll begin a study of asymptotics. What happens when a function gets very, very small or very, very large? How fast does a function go to zero? How quickly to infinity? Quantifying these rates of change will give us a new language, that of the big O, or asymptotic notation.
Let's begin this lesson with a few examples of functions that grow to infinity, but at different rates. Consider, for example, a monomial x to the n, for n a positive integer, and the exponential function e to the x. Both become infinite as x approaches infinity, but at what rate? Well, if we use L'Hopital's rule, then what do we get? In the derivative of the numerator, we have n times x to the n minus 1. The denominator, of course, remains fixed at e to the x. Now, if we continue doing this, applying L'Hopital's rule, then eventually, since n is a positive integer, we will get something times x to the 0. That something is, as you can check, n factorial. Whatever it is, it's a constant. Yet the denominator remains e to the x. What is this limit? It's 0. And what does that mean? It means that the exponential function grows faster than any monomial, and indeed than any polynomial function. Likewise, if we consider, say, the natural logarithm of x, and let's raise it to the nth power and compare it with linear growth, with the monomial x, then what happens? Well, if we apply L'Hopital's rule, we get in the numerator n times the log of x to the n minus first power times the derivative of log of x, which is 1 over x. The denominator, well, the derivative of x is simply 1. So we are left, again, with an indeterminate limit. However, inducting, eventually, what are we going to get? We'll get a constant in the numerator, that constant being, once again, n factorial, the denominator remaining x. This, too, goes to 0, which means that linear growth is faster than logarithmic growth, even logarithmic growth raised to a power. Now, put these together, this means that exponential growth beats polynomial growth, beats logarithmic or even polylogarithmic growth. What else is there? Well, there's an entire world or hierarchy of functional growth as x goes to infinity, beginning with the constant functions that don't grow at all, moving up to logarithmic growth, to linear growth, quadratic growth, cubic growth, all the way to exponential growth. The question remains, is there anything beyond that? What can grow faster than exponential growth? Well, there are indeed worlds beyond that. One simple example being factorial growth. For now, what we want to do is consider the monomials, x to the n for n bigger than 0, and look at their growth, both as x goes to infinity and as x goes to 0. Well, it's not exactly growing there, it's shrinking. But this is extremely interesting because if you look at the hierarchy of functions, as x is going to 0, we see that linear is bigger than quadratic, is bigger than cubic, is bigger than quartic, etc. That is, x to the n plus 1 is less than x to the n, as x is going to 0. That is in contradistinction to what happens as x goes to infinity, where we see that linear growth is much slower than quadratic growth, is much slower than cubic, etc. That is, x to the n plus 1 is bigger than x to the n, as x is getting larger and larger. All right, what are we going to do with that? Well, let's take a look at an example. The limit of 1 minus 2x plus 3x squared over 4 minus 5x plus 6x squared. Let's first consider the limit as x goes to 0. What does that become? Well, this one's really simple. As x is going to 0, all of the higher order terms in x are small, negligible, which means that we simply evaluate this limit and get 1/4, the ratio of the lowest order terms in x. On the other hand, if we look at this same limit as x goes to infinity, we can't do the same thing. What we have to do is switch things around a little bit, factor out the highest order power of x, in this case x squared, cancel that, and what we see left over is 3 minus something small over 6 minus something small, giving a value of 1/2 in the limit. Now, if we compare these two, we see that as x is getting small, it's the lowest order terms that dominate, whereas if x is going to infinity, it's the highest order terms that dominate. This duality is extremely important and can cause confusion, so always pay attention to which way the limit is going. What we really need is a good language for controlling and describing this sort of growth. This is going to be called big O, and it has two forms. One as x goes to infinity, the other as x is going to 0. This is an extremely important and subtle definition. You're going to want to pay attention to this. We say that a function f is in big O of x to the n if, in absolute value, f of x is less than some constant times x to the n. Now, we're not saying exactly what that constant is. It's just some constant. And we're just getting an upper bound. We don't actually care about the value of c. We just want to control the growth. Now, there are two versions of this. One, we could say that this inequality has to hold as x goes to 0, in which case big O of x to the n consists of all functions that approach 0 at least as fast as x to the n. On the other hand, if we look at growth as x goes to infinity, then big O of x to the n consists of those functions that approach infinity no faster than x to the n. In both cases, these are an upper bound. This language replaces the higher order terms that we've used in the past. For example, if we look at the expansion of arctan of x, what is that? The first term in the Taylor series is x. All of the other terms are of higher order in x. Specifically, we could say big O of x squared. Or, more specifically, we could say big O of x cubed. That is a stronger statement. It allows us to be more precise. Or, if we want to expand further, we could say that arctan of x is x minus x cubed over 3 plus big O of x to the 5th. Likewise, as x goes to infinity, we could look at a function like x times square root of 5 plus 3x plus x squared. This is a complicated looking function, But really, it's just x squared plus some other stuff in the limit as x goes to infinity. That other stuff is itself going to infinity, but only at a linear rate. It is in big O of x. If we wanted to be more specific, we could use the binomial series to say that this function is x squared plus 3/2 x plus something in big O of 1. That is, something bounded, something in big O of x to the 0. More generally, instead of talking about big O of x to the n, we could talk about big O of some other function, g of x, if this same inequality holds for some constant c. Let's look at a few examples. In the limit as x goes to 0, the function 5x plus 3x squared is in big O of x, but it's not in big O of x squared. Sine of x is in big O of x, but not in big O of x squared. Log of 1 plus x minus x, as you could see from Taylor expanding, is in big O of x squared, but not in big O of x cubed. 1 minus cosine of x is in big O of x to the 4th, but not in big O of x to the 5th. Square root of x is not in big O of x to the n for any n bigger than 1. It does not go to 0 very quickly at all. On the other hand, e to the minus 1 over x squared is very quickly going to 0. It's in big O of x to the n for all positive n. As x is going to infinity, we have a number of interesting examples as well. Arctan of x is in big O of 1. It's bounded. That means it's also in big O of x to the n for any positive n. X times square root of 1 plus x squared grows quadratically at most, but it is not in big O of x to the 3/2. The log of the hyperbolic sine of x, well, is really in big O of x. It's got linear growth at most. It's not in big O of log of x. It grows too fast for that. Hyperbolic cosine of x is in big O of e to the x. It has exponential growth, but not polynomial growth. Log of x to the 5th can be simplified, and we see that it's really in big O of log x, as well as big O of x to the n for any positive n. Lastly, x to the x is not in big O of constant to the x for any constant, and it's not in big O of x factorial. This is even superfactorial growth. Now, there's a huge subject of asymptotic analysis associated with big O. It has certain rules. The ones that you need to know for this course are the following. If you take something in big O of x to the m and multiply it by something in big O of x to the n, you're going to get something in big O of x to the m plus n, just like multiplying monomials together. This is true whether you're going to 0 or infinity. On the other hand, if you add two functions together, something that has x to the m growth and something that has x to the n growth, then there's a difference. As x goes to 0, your resulting function is in the minimum of m and n. As x goes to infinity, you're looking at big O of x to the maximum of m and n. Let's look at this in the context of an example. As x goes to 0, consider e to the x over 1 minus x. Well, I'm going to write that as the product of two functions. E to the x is 1 plus x plus big O of x squared. Using the geometric series, we see that 1 over 1 minus x is also 1 plus x plus big O of x squared. Now, how do we simplify this? Well, we pretend that everything in sight is just polynomials and multiply them together, even the big O terms. The first term is 1 plus x quantity squared. The next term is 1 plus x times big O of x squared. Of course, we have 2 copies of that, so we'll put a 2 out in front. And our last term is big O of x squared squared. All right, now how do we deal with multiplying by big O? Well, collect together the first term, and then notice that that x squared is in big O of x squared, so we can forget about it. Next, we have 2 times 1 plus x times big O of x squared. Multiplying that out to 2 times big O of x squared plus x times big O of x squared gives us what? Well, we don't care about constants with big O, so forget about that. And x times big O of x squared is big O of x cubed. Lastly, big O of x squared squared is big O of x to the 4th. Now, as x goes to 0, those higher order terms all fall under big O of x squared, and we get a simplification. If we want to make it more interesting, say raising everything to the power alpha, then we could use the binomial series to say that this is 1 plus 2 alpha x plus, well, there's some other terms, but they're all big O of x squared.
This lesson on asymptotics dealt with how to deal with the growth rates of change of a function. And though we're at the end of Chapter 1, this provides a perfect segue into Chapter 2, where we'll codify what we know about rates of change into the notion of a derivative.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 9, Bonus Material. In our main lesson, we considered growth rates of functions and ordered them in a hierarchy as x goes to infinity. This led to a language for discussing and controlling that growth, both as x goes to infinity and as x goes to 0. This language is called big O. Before we get to that, there's one thing that we need to reconsider a little bit. One of the things we discussed was the factorial function, or factorial growth. But what exactly do we mean by factorial functions? What is x factorial when x is not an integer? Well, there is a real definition for it. It's going to look a little complicated. The definition of x factorial is the integral as t goes from 0 to infinity of t to the x times e to the minus t dt. Oh, what in the world is that? Well, we're not going to explain that now. We'll get to that later in this course, maybe in Chapter 3. But for the moment, one thing to know is that this definition satisfies the property that factorials have, namely that x factorial equals x times quantity x minus 1 factorial, at least for x positive. And also, n factorial, for an integer, agrees with this definition. Now, I'm not going to prove that now. We'll talk about that later in the course. What I want to argue is that this factorial growth beats exponential growth. In the case where x is an integer, a positive integer, then we get x factorial being the familiar x times x minus 1 times x minus 2, etc., all the way down. If we look at e to the x, well, this is some number of copies of e multiplied together. Now, for values of x very large, we see that terms in the numerator and terms in the denominator pair perfectly, and almost all of the terms in the numerator are much bigger than the terms in the denominator. And this means that in the limit, as x goes to infinity, we get something that is infinite. That means that x factorial grows much faster than e to the x. If you're curious about this unusual sort of definition, look up information about the gamma function. We'll return to that a little bit later in this course. What I'd like to spend some time on is a bit of discussion about big O. How is this language used? Why is this language used? It is ubiquitous in applied mathematics, and you're going to see it at various points throughout this course. So let's take some time and review and extend what we know. Recall that a function f is said to be in big O of a function g if, in the appropriate limit, f in absolute value is less than g in absolute value times some constant c. We don't care about what the constant is. We just want to know that there is some upper bound. Again, this holds in the limit as x is going to wherever we're interested in looking at. Maybe x is going to 0, or maybe x is going to infinity. One of the reasons big O is so useful is that it forms an efficient language. For example, f is in big O of 1 means the same thing as saying that f is bounded in the limit as x is going to 0 or infinity or whatever. There are other applications as well, real applications. For example, in computer science, one is often interested in specifying how much effort it takes to execute a certain algorithm. This is the subject of computational complexity. Consider the following. Let's say you have two n-digit numbers, and you want to multiply them together. How much work are you going to have to do? How many individual mathematical computations is that going to take? Well, let's consider what it takes to multiply two numbers together using the standard algorithm that you learned in primary school. And let's count this as a function of n, and consider what happens as n is going to infinity. To multiply these two numbers together, I need to take each digit of the second number and multiply it by the entire first number. That is n elementary mathematical operations. Well, maybe it's not n. Maybe we should call it 2n because of the fact that you have to multiply 6 times 3, 18, write the 8, carry the 1, etc. We'll pick some constant times n, but we need to do that for each of the n digits in the second number. Well, we're still not done because we need to take all of those resulting products and add them together. And I'll let you try to figure out how much effort is involved in that addition. It's, some number times n times maybe n minus 1. I don't know. I'm not a computer scientist. I'm a mathematician. But neither I nor the computer scientist needs to worry about these exact constants. If all we care about is what happens as n is going to infinity, we can say that this algorithm is in big O of n squared. It's going to take a quadratic amount of effort. So as your numbers get bigger and bigger, you're doing a lot more work to multiply them together. Is there an algorithm that is better, that is, say, n times log n? Well, that is what big O is good for. Error analysis in engineering, physics, other sciences is another excellent application. Let's say that you know the kinetic energy of your body is 1/2 the mass times the velocity squared. But let's say that your measurement of the velocity has some error associated with it. Epsilon, we'll call that error, and we'll assume that epsilon is very small. What is the induced error in our kinetic energy? Well, of course, if we expand that out, 1/2 mv squared plus m times v times epsilon plus something that is in big O of epsilon squared. What we really care about is the leading order term in epsilon. That is going to dictate what the error to the kinetic energy is. And we can see that that is really the momentum, m times v in this case. Now, other examples are relevant to what we began this lesson with. Let's consider x factorial. We argued that its growth rate is pretty big, that x factorial is not in big O of e to the x. But we can say more. There's a wonderfully useful and powerful formula in mathematics called Stirling's formula that says exactly how fast x factorial grows. One form of this says that log of x factorial equals x times log of x minus x plus some remainder term that is in big O of log of x. Perhaps the stronger version of Stirling's formula will be a bit more transparent. It says that x factorial equals square root of 2 pi x times quantity x over e to the x power times 1 plus something in big O of 1 over x. Now, you don't need to memorize either of these. They're wonderfully useful in probability, in combinatorics, in lots of areas. But what I want you to see is that the appropriate language for expressing how fast x factorial grows as x goes to infinity is big O. Pure mathematics uses big O as well. If we define the function pi of x to be the number of prime numbers less than x. Let's restrict to positive primes, of course, and x is going to be, let's say, integer valued. Doesn't matter. Then, one thing we could say is that the number of primes is big O of x. But that's a vacuous statement. Not every integer is prime. We'd like some idea of how many primes there are. Well, of course, there are infinitely many primes, but we'd like to know a bit finer information. What kind of density do the prime numbers have within the natural numbers? Well, we can use the language of big O to state the prime number theorem, which says that pi of x is to leading order x over log of x. And that's not exactly what it is. That's just the leading order term. But pi of x is x over log x times quantity 1 plus something in big O, 1 over log of x. That's one example of how this language appears in everything from pure mathematics to applied mathematics to the physical and computational sciences. It'll take a little while to get used to this language. It's going to take a bit of practice. Most students find it a bit unlike things that they've learned in the past because of this arbitrary constant. But do a few practice problems, and you'll see big O cropping up later in the course.